also.
Oh, is that right? Yeah, right.
Yes.
Geez, he must be he's so old. Is he still around?
Oh yeah, he's still giving lecture and
amazing.
And yes, I mean this guy's
So
totally
you're
amazing.
his student, right?
Well, no.
No?
No, I mean somehow I told him I met all these great guys, but I always made the wrong choice in taking advice. I wouldn't say wrong choice, but I mean not the best choice. Yeah, but so how we have here is that you get nonlinear optics, you can change the frequency like rubber bios. Rubber bio is what we got PPLN and change the frequency. So
Bob Byers, Stanford, of course.
Yes, that's right. Right. Yeah, he visits Taiwan a couple of times, and then I guess many people are listening by his talk on being those PPLN, periodic pole. This is my opinion. Right, but anyway, so
I've not heard that talk.
Yeah, so how we have that with ultraviolet lasers, right, and then you can do nonlinear optics, so you can have photon citations and harmonic powers. And right now, see, in the old days, right, you need a big machine like this one to generate frequency. And right now, we can just use a photonic crystal fibers to generate sufficient light intensities. Right, and then this is even more technology than maps. Right, we are using tensor fiber. This is still a working pulse for most of the biological lab. But right now, right, this fiber laser is so compact, and then the whole thing is probably just a bit bigger than the notebook size. Right, so you can have one of those machines and close the kind of so fiber and kind of pack anything, right, in a suitcase space. Right, so it's amazing to see how this technology advances and right, even though the physics idea is still the same. So on and so forth. Right, and then this thing is interesting. This is made in Taiwan, and it's a refrigerator. Right, and we put our detector inside. Right, so it cool it to well, it's not operating now, but I mean it can cool to minus 18 degrees C. Right, so the detector will try to generate no noise. So we can do single molecule detection in a time-resolved way. If you just correlate the excitation photon and the emitted photon, so you can do the fluorescence at time.
So you're looking at biological molecules, or what? So you're looking at protons then, or photons? I mean, single molecule. Oh no, I'm sorry, I'm not NMR. So
Just look at how do you get a single molecule?
Well, you just counting, and then from the photon counting provide, photon counting provide, I think 1% looking at the single molecule.
So you're looking at fluorescence coming from a single molecule?
Right, fluorescence, right, among all the countries agent or countries method, it's probably still one of the best.
Yeah, right.
Distinguishing from the future economics, so we can select.
Especially there are so many different fluorescent
Yes. Yes. So in a way, we were trying to do visualizing images. Right. When you are molecular binding or non-binding, using that one, we can try to visualize this single molecule with fluorescent electrons. Right. Rather than traditional ways, just break anything together and totally use it. HPLC or tomography can try to decide what's going on. But it's too invasive and you need much granular molecules. With that, I mean, with photonic method, you can basically tracking all these dynamics or kinetics, single molecule, in vivo, non-invasive.
You will get the time. Really, it's nice to have the temporal information too, because you don't get.
Yeah, exactly.
Lynn Jelinski. Oh, that's her. Does that name ring a bell? She was Lynn Jelinski. She was at Bell Laboratories, and she was interested in looking at how one molecule came in and bound to another molecule. And she basically, she was using these kind of techniques to do that. I don't know whatever happened to her. That was a long time ago.
And right now there are companies specializing in making the light source, electronics, right? So, I mean, if you go back to 20 years ago, there are already people start working on this 20 years ago. You probably take 2 or 3 back. And right now we can basically condense anything, in a single campus. Right? And I will imagine that next year we just try to put something really serious. Yeah.
So do you use genetics to label your molecule?
You mean TFP? Yes. People do that here all the time.
For instance, you can label different molecules with different fluorescence.
Yes.
So you can know exactly what each one is doing.
Yes, I mean a common pair would be the CMP and YP. So that's for one to study that forms the thread pair for fluorescence proteins. Right, but just looking at a single fluorescence protein, and by looking at protein folding or aggregation, you can see the chain of glycan as well on GFP ones.
So you can actually look at the folding process, is that what you're saying?
I mean, if you have a fluorescence protein, and you have many fluorescence proteins, and if they aggregate together, right, there will be a change of glycans.
Yeah.
Right.
It's not really single protein.
Okay, then in that case, it's not single proteins.
That's not so easy to do.
Yeah, there's still challenging. Right, and then almost on the same setup is that there was optical technology called stimulated emission diffusion microscopy. And there's a name Stefan Perl, he was nominated for awards, 3 awards since 2006.
How do you know that?
How do I know that?
Because
Because
he was
it's from
nominated.
I mean, certainly
Well,
the Nobel
I-
Foundation does not publish who's been nominated, and in fact, more than that, the Nobel Foundation, I think, discourages people from
discussing.
right.
Yeah.
So what is this guy's name?
Stefan Perl from Biophotonics, Max Planck Institute. Right, but yeah, I think he started to re-engineering stimulated emission. So basically, just stimulated emission to inhibit the molecule around the diffraction limit.
Okay.
Right. So I mean, you have a diffraction spot, but I mean, if you using a stimulated emission just to plug out the molecule you don't want to see, so then you can improve your spatial resolution numbers. Right, and then you probably heard of Eric Mason. He's also one of the prominent guys. Well, anyway, he was.
I think I left,
just like me,
I left there a long time ago.
Eric Basic and Xiaowei Zhuang and others. They were also using a switching of molecule to reach super resolution.
Super what?
Super resolution, breaking the diffraction limit.
Oh, okay.
Right, breaking the optical diffraction limit without using near field. Right, without the near field, right? Because by switching the molecule, basically you can position the molecule so well. Right, and diffraction limit is that we understand is an accumulation of photons. But if you only look at one molecule at a time, we are not limited by far field diffraction limit photons. So these 3 people come up with 2 or 3 different methods to address this question.
So it keeps getting better and better. The technology keeps getting better.
Yeah, but the amazing thing is that they were using the same principle of stimulated emissions, devised by Einstein. And it was going one way to make lasers, but nobody sort of using it the other way, so we can break the diffraction limit, so we can see the small molecule